Okay, so today's lesson is going to be on electrical energy and mechanical energy. We've talked a lot about energy lately. We're just going to focus in on these two, how they're related and how they can be or how they can produce each other. So in other words, how electrical energy can produce mechanical energy and how mechanical energy can produce electrical energy. Anyway, let's get going. So we have a lot of different concepts to learn about today. We're going to talk about converting between electrical energy and mechanical energy. We'll talk about the relationship between electricity and magnetism. That might sound like it's a totally random thing to throw in here, but it is absolutely essential to understand the connection between electrical and mechanical energy. We'll talk about electromagnets. We'll talk about how motors work. We'll look at the difference between DC electricity, that's direct current, and AC electricity, which is alternating current. And then finally, we'll talk about how electrical generators work. Let's get going. So recall that the purpose of an electrical load is to convert electrical energy into some other form of energy. So a toaster, for example, converts electrical energy into thermal energy, right? Now the focus for today is going to be on the relationship between electrical energy and mechanical energy. Remember, mechanical energy is just basically things that are moving, right? Often we call that kinetic energy. Mechanical energy has got just more components to it. We won't go into the absolute details on that one, but just understand that pretty much anything that involves moving parts in terms of an electrical load, that is going to be something that's converting electricity into mechanical energy. Now, motors are loads that convert electrical energy into mechanical energy. So really that old word motor is basically just something that describes these types of loads. Now, so electricity and magnetism, there is a connection between the two. Danish scientist Hans Christian Ørsted, who lived from 1777 to 1851, conducted an experiment where he deflected a magnetic compass, like a magnetic compass needle, I should say, with a current carrying wire. So this animated picture just down here in the corner is kind of showing this. This person's got a switch right here. So when they're not pressing the switch, there's no current. But as soon as they press the switch down, you're going to notice that the compass immediately flies towards the current carrying wire. And that's because when there's a current passing through the wire, it's actually generating some form of magnetic field, right? And the magnetic field actually alternates around the wire. It orbits around it. So when you put a compass near it, that compass is going to be affected by the presence of that magnetic field. So again, he found there was a relationship between electricity and magnetism. Electric fields can affect magnetic fields. It can actually produce, or rather electric currents can produce magnetic fields is really what that should really say. Anyway, electromagnets. So when electricity flows through a coil of wire, that coil can act as a magnet, right? So we saw even when it wasn't a coil of wire, when it was just a straight wire, it still has a magnetic influence. But coiling the wire around something makes it act as a more stable magnet with a north end and a south end. This is called an electromagnet, or sometimes also a solenoid. Solenoid is another word for electromagnet, basically. It's just used in certain applications. Now, the magnet can be turned off by stopping the flow of electricity. That's really why electromagnets are so useful. In this picture in the bottom right-hand corner, this is like one of those magnets they use at scrap yards. The whole point of this is, this magnet, of course, is connected to these chains, and the chains will actually have electricity that flow through them and then connect to the giant coils of wire that exist within this this like little electromagnet piece thing here, right? And so what they can do is, in the crane that operates this, they can actually turn on or off the electricity that goes through this electromagnet. So if electricity is flowing through here and the whole coil of wire has got electricity coming through it, then it's acting as a magnet, and a very strong one too, because a huge amount of current passing through this is going to produce a really strong magnetic effect. But what's nice about this is it's not a permanent magnet, right? So it's not like a fridge magnet that just stays as a magnet all the time. If you stop flowing electricity through here, the magnet will no longer work. So in other words, they can just flick a switch and all of this stuff will drop down because the magnet is no longer magnetized. Kind of cool. So by switching the flow of current, you can also switch the direction of the magnet. In other words, if we change, like let's say in this bottom left-hand corner picture, notice the negative end is on the right here, positive end's over here, and it's coiling over the wire like so. Basically, what would happen is if you did it this way, you'll have a north end and a south end. But if instead of connecting this end to the negative end of our battery and this end to the positive end, we switched them around, you would find that this would become north and this would become south. And again, that's if we made this negative and this one positive. So you can switch the polarity of the magnet just by switching the direction of the current. Kind of cool. All right, so putting this all together, why are we talking about this? Who cares? Well, this is actually a fundamental idea behind how motors work. So we know that a magnetic field can be made by running electricity through some wire. That was like that compass example I showed you just a minute ago, right? Now imagine a current carrying wire kind of like arranged in like a fly swatter kind of shape, placed between two stationary magnets. Okay, so a north magnet, like a permanent north magnet, and a permanent south magnet. Well, when you have some electricity flowing through here, and just don't get too confused, the arrows are actually showing where the positive flow would go. It's backwards to how we usually think of it. Usually we think of where negative flow goes, but anyway, that's beside the point. When this happens, of course, remember what I said before, your magnetic field will form as like a loop around your wire when it's going in a straight line, right? So there's going to be a loop forming around. This loop basically is going to have an effect where, in this case, it's going to be repelled from the north magnet, at least on this end, and then attracted to the south end. So what's going to happen is, if this thing is allowed to spin, this whole little fly swatter shape kind of thing here, wire, is going to start rotating that way, right? Now, this is, again, just because electricity is flowing through here. Now, there's going to be a little bit of a weird trick. It has to do with this little middle piece right here. Because what happens is, when this flips over, it's just going to be stationary, and this end here is going to be attracted to the south end, and this end here is going to be attracted to the north end, and then that's that. So again, the magnetic field created by the current carrying wire will interact with the stationary magnetic field. It's going to cause this current carrying wire to move, but how can we keep this going? Like, as soon as it flips around, it's going to be stuck there, right? It's going to like just flip around and go, okay, now I'm good. This end's attracted to the south end, and this one's attracted to the north end. We're good now. But how can we keep it rotating? Because if we keep this rotating, imagine like a fan that you would have in your room, for example, that is always rotating. Well, how does that work? Even though it's connected to electricity, how does it keep rotating? Again, it has something to do with this piece right here. I'll show you. So by including a ring with two gaps on its sides, and we call it a split ring commutator, we can keep this process going. Now, this little animated picture here, you might want to really just watch it carefully, because it is easy to miss. But there's brushes that connect from the battery terminal. So the brushes are the contact points leading to the power supply. The coil of wire, the little fly swatter piece that I called it earlier, that's actually called an armature, is allowed to spin between the magnets because it's connected to like a little ring, right? Now, to keep it spinning, this ring, the commutator, causes the direction of the magnetic field in the armature to change every half rotation, so that it's always attracted to and repelled to, from the same magnets. Well, how does it do that? Well, it's really hard to see just by looking at this, but if you watch really carefully, you'll see that there's some gaps, like little splits on the side of it. Now, maybe, you know what, I'll go back to the other slide, because maybe it'll make more sense. Yeah, it will make more sense here. These brushes are stationary. They're just like, literally just brushing this. This little ring can spin around. These brushes aren't going to be attached and moving or anything. They're just brushing against it, so there is just a slight contact point. But as this thing rotates, like let's say it's rotating this way, notice that the positive end is hooked up to this part of the arm, but as it rotates, eventually it'll get to a point where this part of the arm becomes attached to the positive end, right? So then this piece will actually have the positive flow going through it. So the process can continue because the flow of electricity isn't always this way through the wire. As this wire loops around, the flow of electricity will go back and forth between these two pieces because of this split ring. Because as it spins, you'll jump over this gap, and then this positive contact point will be touching this half of the ring. So in other words, this way is where it'll be flowing. Okay, so if we go back to this picture again, I know it is kind of complicated, but as soon as you pass that split ring, notice the direction of the arrows very quickly change, right? And that's because the flow of electricity rapidly changes between the two. Anyway, so this is how all motors work. You don't have to know it in absolute critical detail, but just as long as you know that there's a split ring commutator that changes the flow of electricity, which keeps this attraction and repulsion process going. So in other words, no matter what, at least in this picture, this arm right here on the right-hand side is always attracted to the north end. And then as soon as it gets to the north end, notice it's now being repelled from it, being attracted to the south end. So the loop keeps happening. Every motor that exists works off of this basic principle. All you need to do is just have a ring put in between two stationary magnets and then run an electric current through it, right? And that'll keep it rotating as long as there's electricity flowing. Kind of cool. Oh, if it's gonna let me change, there we go. All right, now AC and DC, or DC and AC, there you go. The type of current electricity we've looked at so far has just been direct current. This is where the electricity only flows in one direction, right? So generally, battery-powered devices are powered by DC electricity. So anything that has a battery, like your remote control or your cell phone or whatever, that is powered by DC electricity. Electricity only flows in one direction. Now, the electricity from outlets in your house is actually something called alternating current, which is a little bit more confusing because the direction of the electron flow rapidly goes back and forth. This picture doesn't do it justice. It's doing it very slowly. What's actually happening is it is going back and forth 60 times per second. Like, this is super rapid. It's going back, forth, back, forth, back, forth, back, forth, like totally super, super fast here. So really the electrons are just switching around, right? Now, the main reason we do this, you might think, why on earth, why? Like, why would we use alternating current? Well, the main reason we use this, because again, it does work as electricity, it's still flowing electrons, is because it's actually a lot easier to transport alternating current over long distances. In the very early days of household electricity, like we're talking about like late 1800s, like the days of Thomas Edison and all them, they initially were using DC electricity, but it was really hard to pump DC electricity to people's homes. And then it was a guy named Nikola Tesla who actually was really advocating for using alternating current. And it's quite fascinating if you want to look it up. Thomas Edison, I'll even just write it out so you can see how they're spelled. Edison and Tesla actually had a lot of arguments and a lot of fights over this. And Edison, as much as he's known for being, you know, quote unquote, the inventor of the light bulb and all that, he was actually not really the nicest guy, at least when it came to dealing with Tesla, because he was trying to discredit Tesla's ideas of using alternating current. He was pushing DC electricity for household devices, despite the fact that it was inferior to AC current. So you might want to look that up. There's a lot of information you can find on that one. It's quite interesting. Whoops, too fast. All right, so transformers. We're really jumping all over the place, but don't worry, we're almost to the end here now. Recall that a transformer is a device that increases or decreases voltage for the purpose of transporting the electricity over long distances. There's those transformers that exist on power poles, and then there's those transformer boxes. They're usually green, and they're usually found like in the alley behind your house kind of thing. Those are transformers, right? So they're just changing the voltage for the purpose of transporting electricity. So Ohm's law says that to change the voltage, you need to change the resistance, because remember, Ohm's law said V equals I times R. So if you wanted to make it higher voltage, you need to make it higher resistance, assuming your current stays the same. Now, resistance is usually inherent in the type of conductor, or in other words, wire that you're using, but we can induce this in different ways, right? Now, the reason this is important is the wire that you use to transport at long distances is often made of the same or very similar material as the wire that goes right into your house. So really, that's no use to us, but we can induce it in a different way. Here's how it can work. If you take basically an iron core, like in the shape of a donut, okay, so like a piece of iron, you know, like mold it into a donut shape, and you coil some wire around it on one end, and then coil fewer wires, or make fewer coils, I should say, on the other end. What you'll do is you'll convert high voltage electricity to low voltage electricity, because this electric field is going to induce one in this coil, which is going to lower the voltage because there's not as many coils. However, if you took a fewer number of coils and then did this to a higher number of coils, you're actually going to increase the voltage, right? That's basically how a transformer works. It's a little bit more complex than that inside the actual transformer itself, but that's the basic principle. All right, now we are almost done here. I know it's been kind of a long go. We're only 13 minutes, but still, it just seems like we've been bouncing all over the place. Generating electricity. Electric generators, so things that produce electricity, work on the exact same principles as electrical motors, except the energy transformation is reversed. Remember, with a motor, you're turning electricity into mechanical energy. With an electric generator, you're turning mechanical energy into electricity, right? So you're taking movement and you're turning it into electricity. So an electric generator is actually going to look pretty much identical to an electric motor. The only difference is you're not hooked up to a battery or something. You're hooked up just to something that can store the electricity, or even just wires to carry it somewhere else, right? So again, with a split ring commutator, like what we had before, if you had like a crank on this and you were actually like cranking and rotating this, you would be inducing an electric current through the wire, right? So even if no electricity is flowing and the thing's just sitting there, if you manually start moving it, that's going to actually induce an electric current. So you'll get electricity flowing through it, which is quite interesting. So this picture, of course, shows it pretty well as well. If they actually attached a crank to it and start rotating this, because it's a ring of wire between two stationary magnets, that'll make it go, oh, I think electricity needs to be produced here now. So electricity will flow. Now, the difference between DC and AC, AC is actually almost easier to generate here. With AC voltage, you don't need a split ring commutator, right? Because as it rotates, remember, As it's spinning, of course, the direction of the electricity will bounce back and forth because of the way it's being attracted or repelled. You don't need to know it too much, just know that a generator works exactly the same way as a motor, okay? So just understand the general setup. All right, so I'll just look through a bunch of different kinds of generators, some of the more common ones that we know of. A wind power generator, of course, we've got lots of these in southern Alberta. Think about it this way. Those wind blades, right, as they rotate, what's happening is that's like pretty much serving as a crank. So inside the generator itself, there's basically some stationary magnets and a rotating coil of wire. That's rotating because of the wind moving the windmill blades, right? So it's the same idea. It's just a rotation in here. Like I'll just even go back. It's a rotation, right, producing electricity. It's the same thing here. There's a rotation going on in here producing electricity. Let's look at a hydroelectric generator. So this is like a cross section of a hydroelectric dam. Basically how it works is they build the dam. There's a huge reservoir up at the top. There is an intake valve, and then there's a slope. I guess they call it a penstock. I actually didn't know that, but there's like a slope so it can gain some momentum coming down. And so when the water's like flowing down this like underground kind of hill here, there's a turbine down there that spins as the water passes through it, and it's spinning, of course, affecting a generator, right? So here's like an even closer cross section. As the water comes in, there's like these blades that the water pushes against, and it causes it to spin, and the spinning, of course, produces that electricity, right? So it's the same idea as a motor. It's just they didn't flow electricity through it. It's producing electricity. Last one we'll look at, coal power. This one's a little bit more crazy. Basically, they have their coal. They burn the coal in a boiler, so a furnace. Now, in this furnace, there's actually water that goes through a bunch of pipes. And the burning coal heats up the water, which produces steam. The steam, of course, comes up through here. And of course, because there's so much pressure coming out of that steam, the steam just shoots through here. And then when the steam comes down, it passes through a turbine. So kind of like the water one, except instead of liquid water, it's gaseous water. So in other words, steam pushing some blades in a turbine. Turbine spins. That, of course, affects a generator. See, there it is. It's going to spin, and then that produces electricity, right? And then they recycle their water and stuff, and the whole big thing. Coal is kind of controversial because it is quite, like, it pollutes a lot, right? You're burning coal. There's smoke that's coming, or sorry, you're burning coal. There's smoke that's coming out of it. So it's a little bit controversial, but it is also very effective, right? So that's why it is still very much in use to this day. What's kind of interesting, I didn't put one in here, just an aside. A coal plant actually works very similar, believe it or not, to a nuclear power plant. A nuclear power plant is really just giving a huge heat source that's heating up some water and then causing steam to rotate some turbines. That's how we produce electricity. That's about it. All right. Anyway, we're done for today. So for practice, please try page 331, questions 1 to 7. I know it kind of seemed like we jumped around today, but when you look at these questions, you'll see it actually wasn't as bad, hopefully, as I think you might think it is. Anyway, as always, if you have any questions, please let me know.